In this video, we will discuss distribution of sample means. A sampling distribution of sample means is a distribution using the means computed from all possible random samples of a specific size taken from a population. The samples are randomly selected with replacement. The sample means, for the most part, will be somewhat different from the population mean, mu. These differences are caused by sampling error. Sampling error is the difference between the sample measure and the corresponding population measure due to the fact that the sample is not a perfect representation of the population. Properties of the distribution of sample means. The mean of the sample means is the same as the mean of the population mean. The standard deviation of the sample means will be smaller than the standard deviation of the population, and it will be equal to the population standard deviation divided by the square root of the sample size. Suppose a professor gave an 8-point quiz to a class of 4 students. The results of the quiz were 2, 6, 4, and 8. So the population mean is mu equals 2 plus 6 plus 4 plus 8, all divided by 4, which is 5. The standard deviation of the population is, we do the standard deviation work, and we get about 2.236. If all samples of size 2 are taken with replacement and the mean of each sample is found, the distribution is this here. And we've got means from 2 to 8 with 3s, 4s, 5s, and 6s along the way. A frequency distribution of the sample means looks like this. There is one mean of 2, 2 of 3, 3 of 4, 4 of 5, 3 of 6, 2 of 7, and 1 of 8. The mean of the sample means, denoted mu of x bar, is the sum of all of the sample means. There are 16 of them total, divided by 16, which is going to be 80 over 16, which is again 5. So that's the same as the population mean. So mu sub chi bar is mu. The standard deviation of the sample means, denoted sigma sub chi bar, is, and we do the same thing with the standard deviation. We're just plugging in all of those values of subtracting the mean and dividing by 16 again. And that's going to be about 1.581, which is the same as the population standard deviation divided by the square root of 2, which is the size of the samples taken. So here we've got sigma chi bar is equal to 2.236 over the square root of 2, and again, that's 1.581. So this tells us that the standard deviation of the sample means is also called the standard error of the means, and that is equal to sigma over the square root of n. The central limit theorem. As sample size n increases without limit, the shape of the distribution of the sample means taken with replacement from a population with mean mu and standard deviation sigma will approach a normal distribution. As previously shown, this distribution will have a mean mu and a standard deviation sigma divided by the square root of n. Two important things to remember about the central limit theorem. When the original variable is normally distributed, the distribution of the sample means will be normally distributed for any sample size n. And when the distribution of the original variable is not normal, a sample size of 30 or more is needed to use a normal distribution to approximate the distribution of the sample means. The larger the sample, the better the approximation will be. The central limit theorem also gives us a new formula we can use, in fact must use, for finding z-values when answering questions about sample means. When we're dealing with distributions of sample means, z is equal to x bar minus mu over sigma divided by the square root of n. So we'll do a couple of examples. It was reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. If 20 children between the ages of 2 and 5 are selected, find the probability that the mean of the number of hours they watch television will be greater than 26.3 hours. So here is our normal distribution, and this is the part of it we're looking for, this tiny part over here. We find the z-value, chi bar minus mu over, sorry, not chi bar, but x bar minus mu. When I see a big X, I automatically assume chi, but it's not chi, it's just X. X bar minus mu over sigma divided by the square root of n. So here that is going to be, I've forgotten to write that in there. 26.3 minus 25 over 3 divided by the square root of 20, which comes out to about 1.94. Using table E, the area to the right of 1.94 is 1 minus 0.9258, which is about 0.0262 or 2.62%. The chances that the mean will be greater than 26.3 hours are 2.62%. And this is really doing exactly what we did in the last section. It's just that now we have to use this other formula for z. One more example. The average drive to work is 9.6 miles. Assume the standard deviation is 1.8 miles. If a random sample of 36 employed people who drive to work are selected, find the probability that the mean of the sample is between 9 and 10 miles. So now we have to find two different z-values. We need to find the z-value for x bar equals 9, which is -2, and the z-value for x bar equals 10, which is 1.33. The corresponding area for z equals -2 is 0.0228. The area for z equals 1.33 is 0.9082. We subtract 0.0228 from 0.9082 and get 0.8854, which is 88.54%. The probability of a sample mean between 9 and 10 miles is 88.54%.